Hello, and welcome to our presentation of Beer's Law, determining concentration using spectrometers. My name is Jessica Sun. Presenting with me today is Yvonne Spector. First, some background on Beer's Law. Beer's Law states that the concentration of a solution is directly proportional to the amount of light absorbed by the solution. What this means is that as concentration increases, the amount of light absorbed also increases. In the equation, big A is the absorbance of the solution, A is the absorptivity, B is the thickness or path length of the sample, and C is the concentration. The derivation of Beer's law is straightforward. Simply divide the absorbing sample into thin slices that are perpendicular to the beam of light, and the light that emerges from each slice is slightly less intense than the light that entered because some of the photons have run into molecules and the sample did not make it to the other side. Once you add up all of the slices, you can see that the light that emerges is much less intense than the light that entered, meaning that the greater concentration in the solution, the greater the amount of light the solution absorbs. The purpose of this lab is to determine the concentration of an unknown solution. We do this using Beer's law to plot points on a graph showing absorbance versus concentration using different concentrations of a solution and the absorbance of each sample. These points will connect to form a line as shown in the graph below. The upward slope of the line shows the direct relationship between absorbance and concentration. We hypothesized a range of potential concentrations based on the clarity or color of the solution, and came up with an estimate by comparing the solution to other solutions of known concentrations. As this picture illustrates, the lighter the solution, the less concentrated. The darker the solution, the more concentrated. Now onto our method. To find the concentration of an unknown solution, we need to have solutions of known concentrations, which we made in a series of dilutions. Next, we use the SpectroVis Plus, a spectrometer that measures the absorbance of a solution placed in it. The data is then graphed and a best linear fit created. Finally, to find the unknown concentration, we measure the absorbance of the solution and match this value up on our absorbance versus concentration graph.
The color tested in this lab was light red, and you can see that the graph shows that almost no red light was absorbed. It was the main color reflected and therefore is the color we see, while a greenish-blue color was absorbed most. No greenish-blue color was seen in the solution. Therefore, it is clear that the less something is absorbed, the more it is reflected, and thus it is the color we see. On this graph, we see the results of concentration versus the amount of light absorbed. The more light absorbed, the darker a solution will be. This graph shows the relationship determined by Beer's law. The higher the concentration at the right end, the more light absorbed. The frequency of light doesn't change at all, but how much light absorbed varies linearly. Because of this linear relationship, we were able to determine that the concentration of the unknown was 0.0469 moles per liter. Our unknown value had a concentration of 0.0469 moles per liter, compared to the mean class value was 0.047194. The median of the class was lower than that, showing that although our results were accurate, they were not precise per se. Our error rate was only 0.623%, less than 1%. The standard deviation for the values of the class were 0.01017, which is a pretty small standard deviation. The outliers were 0.1 moles per liter and 0.0325 moles per liter. There were fewer errors in this lab, leading to more precise results because we were using a computer program and thus there was less human error. However, there could have been a concentration error due to mismeasurement of the initial solution when we were making our initial concentration versus absorbance measurements. There also could have been errors of light diffraction in the tubes. If the tube was turned onto the wrong side, the graph would have showed some weird results. The color a solution reflects, or looks like, is on the opposite side of the absorbed color on the color wheel. For example, if a solution appears, the color wheel helps us predict what frequencies are absorbed in the colors we see.